Imagine shrinking yourself down to the size of a dust motes and then shrinking 10,000 times more. You are now standing on a landscape unlike any city you've ever known, a silicon metropolis of impossible complexity. This is the CPU, and its basic building block is not some futuristic quantum device, but the transistor, the simplest protagonist in our story. We must immediately strip away the illusion that a CPU is a single magical block. That block is actually an ecosystem, a vast interconnected landscape where the only language spoken is binary. And binary, at its core, is a philosophical statement about choice. A transistor is an electronic switch on microscopic gate that can either be on or off. It either allows a current to pass, which we call a 1, or true, or it blocks the current, which we call a 0, or false. That is its entire life's purpose. There's no maybe, no partially, no a little bit of current, only absolute states. In a modern processor, we are not talking about hundreds or even thousands of these switches. We are talking about billions. A typical chip today can house over 50 billion transistors. 50 billion tiny light switches, each flipping on or off millions or billions of times per second. The true genius of the computer lies not in inventing a complex switch, but in recognizing that everything, every image, every sound, every word you read can be represented by simple sequences of true and false. This is the ultimate lesson in breaking down complexity. No matter how overwhelming the problem seems, the underlying reality can always be reduced to a series of simple, distinct, binary choices. By wiring these humble transistors together in strategic patterns, we create the next layer of complexity: logic gates. The AND gate. It's an electronic version of a lock with two keys. Current only flows out, the result is true, if switch A and switch B are both on. The OR gate. It's a backup power system. Current flows out true if switch A or switch B is on. The NOT gate. The ultimate contrarian. If the input is on, the output is OFF, and vice versa. It flips the truth. This is the CPU's most primitive layer, a vast silent network of switches that can only perform the most basic true-false decisions. They have no intelligence, no foresight, no initiative. They only obey the simple, immediate rule of the logic gate they form. Having established our foundation of billions of simple switches, the narrative now zooms out, not to magic, but to simple mathematics. When we wire enough of these logic gates together, especially AND OR and XOR gates in just the right sequence, a miraculous capability emerges: addition. This assembly of gates that can perform rudimentary operations like addition, subtraction, multiplication, which is just repeated addition and comparisons. Is A greater than B? Is called the arithmetic logic unit, or ALU. The ALU is the ultimate workhorse of the CPU. Think of it as a prodigiously fast calculator, a brilliant mathematician trapped in a tiny box. If a CPU had a consciousness, the ALU would be the part that is purely, perfectly obedient, devoid of any independent thought. Consider this: when you add two numbers in a program, that number isn't just calculated magically. It is fed into the ALU. The logic gates within the ALU ripple the binary signals through a series of internal structures called adders. A full 64-bit addition requires the simultaneous, coordinated flipping of thousands of transistors in a process that takes mere nanoseconds. It is crucial to understand the ALU's limitation. It only responds when commanded. It has no initiative, no memory beyond the immediate calculation, and no ability to decide what calculation to do next. It sits in eternal readiness, waiting for a command that arrives in the form of a simple binary code. Add these two values, or compare these two values. This passive nature is essential to the CPU's design. The chip separates the mechanism of calculation, the ALU, from the control of calculation, which we will meet later. This separation of duties is a hallmark of good engineering. The ALU focuses solely on speed and precision in its core functions, leaving the complex strategic decisions to other components. It can perform billions of operations per second, a staggering feat of engineering, yet it is merely a tool. It is the kitchen appliance waiting to be told what recipe to execute. It has no idea why it is adding 2 plus 2, or what the result will be used for. It just calculates instantly and accurately every single time. If the ALU is the calculator, we now need a place to put the numbers just before and just after the calculation. This brings us to the indispensable, often overlooked components that define the CPU's agility: registers and the memory hierarchy. The register is the CPU's immediate scratchpad. Think of it as the tiny, highly polished surface of your desk, where you keep the pen, the paper, and the exact files you are currently working on. These are tiny storage spaces, perhaps only 32 or 64 bits wide, but they are the fastest memory in the entire computer system. They are literally etched onto the same silicon die as the ALU, allowing data to move in and out at the speed of the CPU's clock cycle. When the CPU needs to add two numbers, it doesn't pull them from the warehouse, it pulls them from the registers. The data must be here or the CPU stalls. The registers sit at the absolute pinnacle of a vast and crucial memory hierarchy, a multi-tiered architecture that governs the speed and size of data access. This hierarchy is built on one core brutal trade-off: speed costs size and size costs speed. Let's use an analogy to understand this critical trade-off. Registers, the desk, smallest, fastest, most expensive. The exact papers you are working on. Access time, immediate, 1 clock cycle. Cache, L1, L2, L3. The filing cabinet, larger, slower, less expensive. This is the CPU's short-term memory. L1 is tiny and right next to the ALU. L3 is much bigger but further away on the chip. It holds data that might be needed soon. Access time, very fast, 1 to 20 nanoseconds. RAM, the library, much larger, much slower, much cheaper, the system's main memory. If the data isn't in the cache, the CPU must go to RAM. This is the biggest slowdown most of us experience. Access time, slow, 100 nanoseconds. Long-term storage, the warehouse, archive, largest, slowest, cheapest. Your SSD or hard drive. If the data isn't in RAM, the system must wait for the hard drive to spin up and fetch it. This is a catastrophic stall in CPU terms. Access time, catastrophic, millions of nanoseconds. The system is constantly playing a massive guessing game, trying to preload the data it thinks it will need from the slower tiers, RAM, into the faster tiers, cache and registers. Without a place to hold temporary data, especially the hyperfast, immediately accessible registers, the CPU would be constantly stalled. It would be a phenomenal calculator forced to wait for a warehouse delivery just to add 2 single-digit numbers. The true performance bottleneck in computing is almost never the speed of calculation. It is the latency of fetching the data. We have our raw materials, transistors, our workhorse, the ALU, and our workspace, registers and memory. But how does this collection of obedient parts actually do something useful, like displaying a web page or running a game? The key is the instruction. At this stage, the reader must learn that a CPU's actions are never spontaneous. They follow explicit, step-by-step instructions. A CPU is by design incredibly simple-minded. It doesn't understand open the browser or calculate the orbital mechanics. It only understands a very limited vocabulary of simple, granular commands called its instruction set. Programs, which we see as complex, fluid software, are portrayed internally as nothing more than long, structured chains of these simple commands, a massive detailed recipe. The CPU's vocabulary is short and repetitive, consisting mainly of commands like load, get a value from memory, RAM or cache, and put it into a register. Store, take a value from a register and save it back into memory. ADDSUBCMP, perform an arithmetic logic unit operation. JUMP, stop executing the next instruction in the sequence and go to a new location in the program list. This is where the grand illusion of software breaks down. Even the most complex action you can imagine, say, clicking the jump button in a video game, is not a single event to the CPU. It is a long, highly structured, sequential list of simple instructions. Load. Load the XY coordinates of the mouse click into register A and B. Load. Load the XY coordinates of the jump button. Boundary into register C and DCMP. Compare register A to C. Is the X coordinate inside the button? Jump if false. If the comparison fails, jump to the end of this routine. Ignore the click. LOAD. Load the constant value for jump height into register EADD. Add registered E to the character's current Z position using the ALU. Store. Store the new Z position back into the memory location for the character. JUMP. Jump to the next main instruction. All software, from the operating system to your favorite application, is just structured lists of these simple operations executed in sequence. This level shows the breathtaking efficiency that arises when simple, repeatable rules are applied billions of times per second. We have the recipe, instructions, the ingredients, data in memory, and the chef, the ALU. Now we need the chef's discipline, the rhythmic, unceasing process that turns a static list of instructions into a dynamic, flowing computation. This is the Fetch-Decode-Execute Cycle, the CPU's heartbeat. This loop repeats millions, even billions of times per second, driven by the steady pulse of the CPU's clock. The clock is a crystal that dictates the tempo, ensuring all components operate in perfect synchronicity. One cycle is one tick of the clock. The cycle begins by retrieving the next instruction from memory. A special internal register, the program counter, PC, holds the address of the next instruction to be run. The CPU fetches the raw binary code at that address and pulls it into a temporary instruction register. This is like the chef pulling the next line of the recipe off the page. Once fetched, the binary code is just a sequence of 1 south and 0 south. The CPU's control unit must now interpret what that code means. It looks at the opcode, the command part of the instruction, and figures out, this sequence means ADD. And these following bits tell me which registers to add. This is like the chef reading the line, combine flour and eggs, and preparing the necessary action and ingredients. Finally, the CPU performs the required action. If the instruction was an ADD, the control unit sends signals to the ALU and the necessary registers, telling the ALU to perform the calculation. If the instruction was a jump, the control unit simply changes the value in the program counter to point to a new address. The result of the operation is stored back in a register. This is the actual physical action of combining the ingredients. And then, the cycle immediately begins again. Fetch, decode, execute, fetch, decode, execute. This is the profound, simple genius of the machine. The story highlights that every processor, from the vintage machines of the 70s to the modern giants of today, relies on this same fundamental, three-part cycle. It is the unwavering, non-negotiable discipline that allows complexity to emerge from simplicity. The single Fetch-Decode-Execute cycle is elegant, but by the 1980s, engineers realized it was creating a massive inefficiency. While one part of the CPU was executing instruction, the other parts were sitting idle waiting for instruction B to start. It was like a factory where every machine had to wait for the previous step to fully complete before starting its own. The story escalates by revealing how modern CPUs boost performance, not by making the clock faster, there are physical heat limits, but by introducing intelligent overlap, pipelining. Pipelining treats the FDE cycle like an assembly line. An instruction is broken down into its constituent stages, or even more granular stages like fetch, register read, execute, memory access, register write-back, while instruction 1 is in the execute stage. Instruction 2 can be in the decode stage. Instruction 3 can be in the fetch stage. The pipeline allows multiple instructions to be in different stages simultaneously, dramatically increasing throughput. Instead of one instruction completing every 3 clock cycles, the goal is for one instruction to finish every single clock cycle once the pipeline is full. The biggest threat to this beautifully smooth assembly line is a branch instruction, a jump command. If the CPU is happily pipelining instructions and then suddenly hits a jump, the entire pipeline must be flushed because all the work it was doing on the subsequent instructions, instructions 2, 3, and 4, is now useless. The CPU has to jump to a completely different part of the program. To combat this, modern CPUs employ branch prediction. This is where true engineering-based intelligence comes into play. The CPU uses sophisticated algorithms and historical data to guess which path the program is likely to take, which jump will be executed. If the prediction is correct, the pipeline stays full and performance soars. If the prediction is wrong, the pipeline is flushed and the CPU suffers a costly stall. It's a high-stakes bet, but one that pays off most of the time, keeping the assembly line humming. Finally, the story introduces the most intuitive leap in performance: multi-core designs. If one CPU core, one FDE engine, is fast, then 2 independent cores running simultaneously must be twice as fast. Multi-core processing simply multiplies computing ability by allowing several independent FDE cycles to run at once. This is the foundation of true multitasking. One core can handle your word processor while another core handles your music streaming. and the third handles the operating system maintenance. This level explains why contemporary chips can juggle many tasks fluidly, because they are not one engine working harder, but a team of highly efficient, pipelined engines working in parallel. We have ascended from the single switch to the highly efficient, multi-core processing engine. The final level of our odyssey is the architectural one, the grand blueprint where everything integrates into a coherent, unified system. The narrative reveals the ultimate truth of modern computing. The most advanced chips today are not just CPUs anymore. They are systems on a chip, SoCs. Look at Apple's M-series chips, for instance. They are the culmination of this architectural thinking. The SoC is a single piece of silicon containing not only the multi-core CPUs we just explored, but also GPUs, graphics processing units, specialized engines designed for massive parallel processing of visual data, neural engines, ML accelerators, custom hardware optimized for the specific math required by machine learning algorithms, unified cache and controllers, the elaborate traffic cop system that manages the flow of data between all these engines and the memory. This approach, integrating everything onto one piece of silicon, dramatically reduces the energy required to move data and radically increases performance by placing the memory hierarchy, L1, L2, L3 caches, in the most advantageous locations relative to all the processors. At the core of this final layer lies a philosophical debate embedded in the design itself, the tension between reduced instruction set computing, RISC, and complex instruction set computing, CISC. CISC, for example, traditional Intel AMD, the goal is to make the instructions themselves very powerful. One single CISC instruction might execute an entire complex operation, like load, ADD, and store. It's powerful, but the instruction takes many clock cycles to complete and makes the decode unit very complex. It's like a chef who knows 100 complex custom recipes perfectly. RISC, for example, ARM M1. The goal is to make the instructions incredibly simple and uniform, like load or ADD. This makes the decode unit simple and allows for much easier and deeper pipelining. It's like a chef who knows only 20 simple actions, but can combine them to create any recipe in the world, extremely fast and efficiently. The modern trend, exemplified by the M1, is toward the RISC philosophy, favoring many, simple, fast instructions over fewer, complex, slow ones. This design decision impacts everything from power consumption, lower, to efficiency, higher. This culmination shows how countless engineering decisions, from power management and cooling to the design of the compiler, the software that translates high-level code into those simple instructions, merge into a unified computing machine. The system is managed by the unseen hand of out-of-order execution, which constantly monitors the instruction stream and rearranges the instructions on the fly to keep the ALU and pipelines running at 100% capacity, regardless of the original program sequence. It is a world of constant motion, precise control, and unified purpose. The transistor, the tiny switch from level 1, is now the essential atom in a digital city defined by its elegant architecture. The ultimate lesson of the CPU is this: true intelligence and complexity are not born from complicated parts, but from the relentless, disciplined, and unified execution of simple rules. Advice drawn from the story for daily life. Simplify your choices, the transistor. When facing a complex decision, force yourself to reduce it to a simple binary true-false choice to overcome analysis paralysis. Separate planning from execution, the ALU. Do not strategize while you work. Plan your tasks and then execute them with perfect, obedient focus. Protect your registers, memory hierarchy. Keep your most vital data, your immediate goal, your critical action step, right at the front of your mind. Eliminate distractions that force a costly trip to RAM. Write your program instructions. Break every large goal into a sequential list of tiny, simple, executable instructions. Load, ADD, store. Cultivate a cycle, FDE. Adopt a disciplined daily rhythm, a non-negotiable routine for fetching, decoding, and executing your most important work. Thank you so much for joining me on this deep dive today. Wishing you all the very best of health and happiness. And if you found this journey as fascinating as I did, please consider hitting that subscribe button and ringing the bell so you don't miss our next adventure into the heart of technology.